So in this lesson, we are going to learn about proportional and non-proportional relationships. This is chapter 1, lesson 4, and we go back to our essential question. Essential question is, how can you show that two objects are proportional? In the last lessons, we have not yet determined, or we have not yet defined what the word proportional means. So in this lesson, we are going to understand and learn the definition of what it means to be proportional, okay, non-proportional, and what equivalent ratios are. Okay, so let's take a look at this real world link and see how it works. Miss Cochran is planning a year-end pizza party for her students. Ace Pizza offers free delivery and charges $8 per medium pizza. Okay, so we want to complete the table to determine the cost for different numbers of pizzas ordered. So we know for a fact that each pizza is $8. Okay, so that means for the cost for one pizza is $8. So therefore the cost for two pizzas would be $16 if I multiply 2 times 8. For the cost for three pizzas would be $24. 3 times 8, 3 pizzas, or 8 plus 8 plus 8. Cost for 4 pizzas would be $32. And the cost for 5 pizzas will be $40. Okay, so now we have completed our table in terms of the number of pizzas and the amount you need to pay for that number of pizzas. So number 2, let's take a look at number 2. It says here, for each number of pizzas, fill in the boxes to write the relationship of the cost, okay, of pizzas to the ratio in simplest form. So when you see here the relationship of the cost and the number of pizzas, that means our numerator will be the cost and the denominator will be the number of pizzas. So this is our numerator, this is our denominator right there. So we have 16 over 2, $16 for 2 pizzas. If I simplify that, okay, that'll become 8 over 1. That means dividing both sides of dividing the numerator and the denominator by 2. Okay, same thing here. If I have $24 for 3 pizzas, if I simplify that, divide the numerator and denominator by 3, okay, this will be 8 over 1 as well. Okay, and on the last table, second to the last table, you have $32 for 4 pizzas. And again, if I get the greatest common factor of 32 and 4, which is equal to 4, divide both 32 and 4 by 4, this also becomes 8 over 1. And on the last, okay, column, you have $40 for 5 pizzas. So we're going to write $40 for 5 pizzas. And again, if I simplify 40 over 5, this also becomes 8 over 1. Now, what do we notice here? So 8 over 1, 8 over 1, 8 over 1, 8 over 1. Which brings us to the third question. What do you notice about the simplified ratios? Again, the ratios are equal. Okay? So here, the ratios are equal. Okay? Each ratio is equal to 8. So each ratio is equal to 8. Okay? Because 8 over 1 is the same as 8. So we answer that real world link here. Let's take a look at the key concept for this lesson. So now we can move on to defining a few terms here, proportional and non-proportional. Okay? So let's take a look at, let's read the first paragraph here. Two quantities are proportional. Okay? Two quantities are proportional if they have a constant ratio or a unit rate. Again, take a look at this. Two quantities are proportional if they have a constant ratio or a unit rate. Okay? So If they have a constant ratio or unit rate, two quantities are said to be proportional. Okay, holds true for the opposite for relationships in which this ratio is not constant. So if you don't have a constant ratio, the two quantities are considered to be non-proportional. Okay, so let's take a look at the pizza example. And in the pizza example, okay, uh, the cost of an order is proportional to the number of pizzas ordered. Why is that? Because again, okay, if we look at the cost of the order over the pizzas ordered, okay, they're all equal to 8 over 1. So from the previous page, we know that 16 over 2 is 8 over 1, 24 over 3 is 8 over 1, 32 over 4 is 8 over 1, and 40 over 5 is 8 over 1. Or what it's saying is that, okay, it's $8 per pizzas. Okay? Now, what do you call these types of ratios right here? If they are all equal to each other, okay, that means um, these ratios are considered to be equivalent ratios. So all of the ratios, okay, right here are considered to be equivalent ratios because they all have the same value. Okay? So 8 over 1, 16 over 2, 24 over 3, 32 over 4, and 40 over 5 are all considered to be equivalent ratios because they all have the same value. Okay, let's take a look at example number 1 and see how this works. Andrew earns $18 per hour for mowing lawns. Is the amount of money he earns proportional to the number of hours he spends mowing? Explain. Again, Andrew earns $18 per hour for mowing lawns. So the question is the amount of money he earns proportional to the number of hours he spends mowing? Okay? So first and foremost, what we need to do here is we need to find the amount of money he earns for working a different number of hours. Okay? We need to make a table to show these amounts. And if we create this table, this is what we're going to see. So basically, this is what this table is saying. For every hour that he mows the lawn, he earns $18. That's what it's saying here. $18 per hour for mowing lawns. So for 2 hours, he earns $36. For 3 hours, he earns $54. And for 4 hours, Andrew earns $72. Now, what can you also see is that for each number of hours that he worked, okay, we can write a relationship for the amount he earned, okay, and hour as a ratio in simplest form. So we can actually write all these ratios in simplest form, and this is what we get. Okay? So we have 18 hours per hour, okay? Or the simplest form of 18 over 1 is equal to 8. We also know that 36 over 2 is equal to 18 over 1, or 18. 54 over 3 again is equal to 18 over 1, or simply 18. And 72 over 4 is the same as 18 over 1, or 18. Okay? Now what do we notice about all these ratios? They all have, okay, all of these ratios, okay, between the two quantities can be simplified to 18. So if I simplify all these ratios, 36 over 2, 54 over 3, 72 over 4, even 18 over 1, I can simplify them all to be 18. So knowing that they have the same ratio according to our definition, okay, the amount of money he earns is proportional to the number of hours he spends mowing. Okay? So do the got it problem and see if you understand that particular example. Okay? Again, make a table. Use a table for you to be able to determine if it's proportional or not. Okay, let's take a look at the next example. Example number 2. Uptown Tickets charges $7 per baseball game ticket plus $3 processing fee per order. Okay? Is the cost of an order proportional to the number of tickets ordered? Explain. Again, let's read this again. So we have Uptown Tickets. They cost $7 per baseball game per baseball game ticket. Okay? And then you have an added $3 for processing fee per order. Okay? So the question is the cost, okay, of an order proportional to the number of tickets ordered? We need to explain that, and again we need to use a table. Let's see how the table works. Okay, so the cost is here. Okay, $10 per one ticket ordered. Why is that? Because $7. Okay, $7 plus $3 will equal $10, and that's how you got 10 per one ticket. The $3 is the processing fee. So every single time you buy a baseball game ticket, you add $3 for the processing fee. Now, if you have two tickets, if you buy two tickets, okay, since each, okay, how did we get to 17? See, each ticket costs $7. That's going to be 7 plus 7, which is two tickets, and you add the processing fee of $3, which will give you 17. Okay, same thing with 24. You have three tickets now, 7 plus 7 plus 7, then add the processing fee, which gives you 24. And the same thing happens with if you buy 4 tickets. 4 tickets is 7 plus 7 plus 7 plus 7, add the processing fee, will give you 31. Okay? So let's analyze the ratios and let's see if we have a constant ratio or not. So for each number of tickets, write the relationship of the cost and number of tickets as the ratio in simplest form. So basically what we need to do is we need to get all of these, write it as a ratio, and put it in simplest form. If we do that, this is what we're going to come out with. Okay? So the cost of an order, start with here, be $10 per one ticket, or 10. So that is the simplest form of this ratio. 17 over 2. Okay? If I divide 17 by 2, I get 8.5. So this is again the simplest form of this ratio as a decimal. Okay? The simplest form of 24 over 3 is 8. And the simplest form of 31 over 4 as a decimal is 7.75. Now, what do you notice? The ratios are not the same. So if that is the case, okay, since the ratios of the two quantities are not the same, the cost of an order is not proportional to the number of tickets ordered. So again, look at the steps that we did here. We first created a table, okay? And then the second step is we simplified all the ratios on that table, okay? And if we find that the simplest form, okay, is not constant, the simplest form, the ratio is not constant, or you don't have a unit rate, okay, that means it is not proportional. If they are constant or you have a unit rate, then it is considered to be proportional. But in this case, it is not proportional. Okay? Let's take a look at example number 3. You can use the recipe shown to make fruit punch. Is the amount of sugar, okay, used proportional to the amount of mix used? So this is what we're looking at. So you have 1/2 cup of sugar, 1 envelope of mix, 2 quarts of water. That is the recipe for our fruit punch. Now the question is the amount of sugar used proportional to the amount of mix used? So basically this is what we're looking at. Is the amount of sugar used proportional to the amount of mix used? So for every 1/2 cup of sugar, okay, you use 1 envelope of mix. Okay, and let's see how this works. Again, we create a table for this. So for this one, we create a table, find the amount of sugar and mix needed for different numbers of batches, make a table to help you solve. So let's say we are going to create a table for different batches of mix. Okay, so we start off our mix with cups of sugar and the number of envelopes, okay, of the mix. So we know for a fact for every 1/2 cup of sugar, okay, we have 1 envelope of mix. For every 1 cup of sugar, we have 2 envelopes of mix. For every 3 cups, for every 1 and 1/2 cups of sugar, you have 3 envelopes of mix. And finally, for every 2 cups of sugar, we need to use 4 envelopes of mix. So again, we have our table. These are the ratios that we are going to work with: 1/2 over 1, 1 over 2, 1 and 1/2 over 3, 2 over 4. We want to find out if we can get a common ratio or a unit rate for this. Okay? So, for each number of cups of sugar, write the relationship of the cups and the number of envelopes of mix as a ratio in simplest form. So we go back here, and this is what we need to do. Our numerator will be the number of cups of sugar. The denominator will be the envelopes of mix. So for every 1 envelope of mix, right here, okay, 1 and 1/2 over 1 is the same as 0.5. Remember from chapter, the earlier lesson about complex fraction, okay, when we say 1 and 1/2, 1/2 over 1, it is the same as 1/2 divided by, okay, 1, or 1/2. Get the reciprocal of 1 over 1, which is the same as 1 over 1, or simply 1/2. If I make this into a decimal, okay, this will equal 0.5. And that's what you got right there. So let's take a look at the next one. We know that 1/2 also is equal to 0.5. 1 and 1/2 over 3 is the same thing. Again, 1 and 1/2 over 3, okay, is the same as, we make this into an improper fraction, this one right here. So this becomes 3 over 2 over 3, or the same as 3 over 2 divided by 3, or the same as 3 over 2 multiplied by 1/3. Cancel that one out, cancel that one out, and we end up with 1/2 or 0.5. Same thing. And we know that 2/4 is also the same as 1/2 or 0.5. Now if you notice, we have a constant ratio of 0.5. Okay? So in this case, all of the ratios between the two quantities can be simplified to 0.5. So the amount of mix used is proportional to the amount of sugar used. Okay? Alright, do the got it, letter B. Then let's see if you understand the lesson. The table has been drawn for you, so all you need to do is complete the table as you answer that problem. Okay? Let's take a look at the last example, which is of course always a word problem, a different kind of word problem. So in this example, we're talking about two different tables. The table shown, let me show you the table shown, represent the number of pages Martin and Gabriel read over time. Which situation represents a proportional relationship between the time spent reading and the number of pages read? Explain. Okay, so let's look at the two tables first. We have the pages that Martin read and the time, the pages that Gabriel read and the time. So Martin read 2 pages, and it took him 5 minutes to read the 2 pages. And when he read 4 pages, it took him 10 minutes. When he read 6 pages, it took him 15 minutes. Gabriel, on the other hand, read 3 pages, took him 5 minutes, 4 pages for 10 minutes, and 7 pages for 15 minutes. Okay? So first and foremost, we need to write the ratios for each time period in simplest form. Basically, we want to simplify 2 over 5, 4 over 10, 6 over 15, 3 over 5, 4 over 10, 7 over 15. Okay, and we want to find out which has a common ratio. Okay, so our numerator again will be the number of pages. Our denominator will be the time in minutes. So let's take a look at the pages Martin read, which is 2/5, okay, 4/10, and 6 over 15. If you notice, they all simplify to 2/5. So 4/10 simplify to 2/5, 6 over 15 simplify to 2/5. So you notice here you can already see a common ratio. Okay, on the other side, the pages that Gabriel read, you have 3/5, 4/10, 2/5, and 7/15. You notice that they have different ratios. 4/10 is the same as 2/5, but it's not the same as 3/5, nor is it the same as 7 over 15. Okay, so in this case, okay, all of the ratios between Martin's quantities are 2/5. So Martin's reading rate represents a proportional relationship. So Martin's reading rate right here is the one that represents a proportional relationship. Okay, so that's the end of the lesson. Please answer the last question for this video. Thank you for watching.